In the last lecture we went through some properties of vectors in 2 dimensions, vectors which lived on a plane, the infinite Euclidean plane, and we looked at how unit vectors changed when you went from the Cartesian basis to the basis in which you had plane polar coordinates, and we looked a little bit at kinematics in a plane. Today we are going to start on vectors in 3 dimensions. After all, we live in 3-dimensional space, and there are a large number of interesting properties of vectors which are physically very important. Therefore, we are going to devote a little bit of time and attention to studying these properties and analyzing what vectors do in 3 dimensions in different ways. Now the first point is that to define a vector in 3-dimensional Euclidean space, we use the same strategy as we used in earlier cases in the plane, for instance, by saying that under a coordinate transformation of the Cartesian coordinates x, y, z, under a rotation of the coordinate axes, these coordinates went to some new coordinates x prime, y prime, z prime, where these 3 quantities are given as specific linear combinations of x, y and z, the original coordinates, when I make a rotation of the coordinate axis about the origin. So here is my coordinate system, the original one with x, y and z, and the idea is you rotate this coordinate system to make it orient in some other direction, and in the new coordinate system a given physical point which has coordinates x, y, z in the original system has new coordinates x prime, y prime, z prime, which are linear combinations of x, y and z. So the idea is that if you had another coordinate system which perhaps looked like this, and that was x prime, this is y prime and that is z prime, then there is a formula which connects these 3 new coordinates to the old coordinates, and in symbols this is written in the following way. This goes, any position vector r goes to r prime, which is equal to some rotation matrix acting on r. When I write this r as a column vector, 3 by 1 column vector, then this r is a 3 by 3 matrix which multiplies this 3 by 1 column vector to produce a 3 by 1 column vector in the prime coordinates. Now this rotation matrix is more complicated than the 2-dimensional rotation matrix which we wrote down, where only one angle was involved. There was a theta and there was a cos theta, sin theta, minus sin theta, cos theta was the matrix, and that was it. But now we have a much more complicated situation, because to specify the new coordinates or the rotation, I rotate about some direction in space through a certain angle. So really speaking, this rotation matrix in general, you need to specify an axis of rotation, a unit vector which tells you the direction of the axis, and you need an angle psi through which you rotate. So you have 2 parameters here to tell you what the components of this unit vector are. Because it is a unit vector, the third component can be written in terms of the first 2, and then you need an angle. So physically what it says is, if you have a direction in space as given by this piece of chalk, then you can rotate about that direction in a plane perpendicular to it through an angle psi, and that gives me the rotation itself. And this is specified by some 3 by 3 matrix which is fairly intricate, and I will not write this down, but the end result will be that x prime and y prime and z prime will be linear combinations, homogeneous linear combinations of x, y and z in general. A very simple case would be where I actually have a coordinate system. Here is x, here is y, here is z, and I rotate about the z axis through a certain angle psi. So all that happens is that this x becomes x prime through this angle psi, the y goes in and becomes through the same angle psi, that is y prime, and z prime is the same as z. And that is a particularly simple case of a rotation, and we can write the matrix down in that case, because then r, the unit vector is the z direction Ez and psi, and this will of course be cos psi, sin psi and 0 here, minus sin psi cos psi and 0 here, 0, 0 and 1 here, because now it is very clear that all that happens is, since the z coordinate is unaffected, the x and y coordinates would act as if, or transform as if, there is a rotation in the xy plane through an angle psi, for which we know the formulas. So this matrix, when it acts on x, y and z, which is the 3 by 1 column vector representing a point in 3-dimensional space, produces for you, so this thing acting on r is equal to this. This produces for you the new coordinates x prime, y prime and z prime. And of course you see immediately that x prime is x cos psi plus y sin psi plus 0, y prime is minus x sin psi plus y cos psi plus 0, and z prime is equal to 0 plus 0 plus z. So it is clear that you have preserved the fact that z prime and z do not change at all, because if you rotate about the z axis, then the z coordinate of any point does not change at all. So that is the matrix in this very simple case. But in the more complicated case, where this is an arbitrary direction, the formula gets much more complicated. We do not need it at the moment at all. Okay. So much for what happens to a coordinate point. Now what is a vector? A vector is a point which transforms by definition. The vector is a set of 3 numbers, the 3 components, which transform under a rotation in exactly the same way as the coordinates do. So if this quantity, if u is a vector, then under a rotation u prime must be equal to the same matrix on the components of u, the same as governs the transformation of the coordinates, and I am not going to write it down explicitly. So this says ux prime is a linear combination of ux, uy, uz and so on, in exactly the same way as x prime, y prime, z prime are linear combinations of x, y, z. That is now the correct definition of what a vector is in 3 dimensions. So once you have that in place, then we can create the dot product between 2 vectors, and we can do a large number of other things. But since we are going to change bases and so on, let me write down what the Cartesian basis is, and keep that in mind. We will go on to other coordinate systems as well. So the Cartesian basis consists of this triplet of vectors Ez, which in elementary notation is sometimes written as I, J, K. I prefer, for reasons I explained already, I prefer this notation simply because we will go to other frames, other coordinate systems, in which case I would like to be able to find out, to look at a glance, tell which unit vector I am talking about. Therefore I prefer to write it in this the Cartesian basis in this form. Okay. Now we also define what is called a scalar product or dot product between 2 vectors, and that was a scalar because of the following reason. So if you have a vector A which has got components Ax, Ay, Az, and a vector B which has components Bx, By and Bz, then the so called dot product or scalar product of A and B written as A dot B is by definition equal to Ax Bx plus Ay By plus Az Bz, and this is the definition. It is defined in this fashion. Now exactly as we did in 2 dimensions, we could in principle write down what are the primed values Ax prime, Bx prime, Cx prime, etc., and Ay prime, By prime, etc., and we can verify that this is equal to A prime dot B prime, which is Ax prime, Bx prime plus Ay prime, By prime. There are more elegant ways of verifying it using just the properties of this matrix R, the rotation matrix R, but I am not going to go into that here. It is a matter of a little bit of algebra, but it is easy to show that this quantity A dot B does not change under a rotation, and therefore since it is the same in the unprimed and primed coordinates, it is a scalar. This thing here is a scalar quantity. In particular, if B is set equal to A, then this number A dot A for any vector is also written as A squared, and that is of course by definition AX squared plus AY squared plus AZ squared, and that is a scalar. This quantity here, the magnitude of square of the magnitude of a vector is a scalar. Okay. A special case of that is when you have Ax is the same as x, Ay is the same as y, and so on, and then of course R squared is x squared plus y squared plus z squared, and that is a scalar. So the distance from the origin to any point does not change if the coordinate system is rotated about the origin. A little generalization of that, the distance between any 2 points in space does not change if the coordinate system is rotated about the origin, or any point for that matter. So these are all scalars, these quantities are all scalars, and we have the concept of a scalar product. But in 3 dimensions something else happens, something very special happens, and that is the following. But before that we will answer this question of what happens if instead of a proper rotation about the origin, I look at an improper transformation similar to the reflection I looked at in 2 dimensions. So suppose I look at a transformation under which x goes to minus x, y goes to minus y, and z goes to minus z. This is like saying that I take a coordinate system of this kind, x, y and z, a right handed coordinate system, this is the origin, and now I look at x comes sticking out of the board, so I go in and that is my x prime. This y is flipped in direction and that is my y prime, and the z is flipped in direction and that is my z prime here. What about that coordinate system? Now it is a matter for you to verify that if I take my right hand and I call this x, y and z, there is no rotation that I can do which will take me to this new coordinate system, x prime, y prime and z prime. So this was the original x prime has gone inside, y prime is on the left and z prime is pointing down. There is no way in which you can reach that coordinate system from the original coordinate system by a rotation. This is called a parity transformation, where you have changed r goes to the new r prime which is equal to minus r. So a vector changes sign under a parity transformation. This thing is called parity. Now once this happens, a general vector, if it behaves exactly like the coordinates under these transformations, will therefore change sign. Each component will change sign under coordinate transformations. On the other hand, what happens to the scalar product? Well, if A goes to minus A and B goes to minus B, A dot B remains unchanged. It is exactly the same under a parity transformation, which is why it is called a scalar. Had it changed sign, I would have called it a pseudo scalar, but it does not change sign, so this thing is indeed a scalar here. Alright, so now let us ask, what are the possible vectors? What do these things look like? Well, let us write down a physical table here of physical quantities which are vectors in this sense and which we know from other means, from other information are like vectors. So here is a set of vectors that we know. Position R, the position of a point in space or a particle in space is a vector. Then the velocity, let us look at some physical quantities. Velocity v, this is equal to dr over dt, the rate of change of this position with respect to time, and there is an r here, so it is obviously a vector once again, and it is also a vector in the same sense under parity that the position is, because t does not get affected by changing x to minus x, y to minus y, etc. So that is a proper vector. What about acceleration? A. This is the second derivative, what is the derivative of the velocity, and that of course it is the second derivative of the position, first derivative of the velocity. That too is a proper vector. It will change sign under a parity transformation and otherwise behave under a rotation exactly as a vector does, as the position does. Okay. What about a quantity like momentum, linear momentum, P? Well, in the naive definition of a momentum for a particle, this is equal to m times the velocity, and that quantity m is a constant, it is a scalar, and therefore this is also a vector, behaves also exactly like the velocity does under rotations, under parity transformations and so on. Force, F. What would that do? Well, we need an equation which connects force to some of the things we already know about, and we know Newton's third law, which tells us the mass times the acceleration is equal to the force. So since we have a connection of that kind, we say this quantity is like a vector, that is a scalar, so this quantity is a vector, a proper vector. So certainly this is a proper vector. Okay. And so on. We can create a whole list of these vectors and say that they all would have transformation properties which are known once you know the transformation property of the coordinates under rotations. Okay. But now comes the curiosity, which is valid only in 3 dimensions, a peculiarity of 3 dimensions, rather similar to what we found in 2 dimensions, but 3 has its own special nature, and that is the following. You discover that if you took 2 vectors of this kind, then just as in the case of 2 dimensions, recall that we had ax, ay and bx, by for 2 vectors, and then I said, look, ax bx plus ay by was a scalar in 2 dimensions, and then we pointed out that ax by minus ay bx behaved under a rotation of the coordinate axis about the origin in the xy plane like a scalar, did not change, but under a reflection x to minus x or y to minus y, it changed sign, and this became a pseudo scalar. This antisymmetric combination became a pseudo scalar. But now in 3 dimensions we have a more general possibility. So in addition to the scalar product, which is ax bx plus ay by plus az bz, we also have the possibility of combinations like ay bz minus az by, but we have 2 more such combinations possible, and that is az bx minus ax bz, and the third possibility is ax by minus ay bx. And those are the only possibilities for these antisymmetric combinations of one component of A with another component of B, and then in the reverse order, this kind. So we have 3 such quantities which are the analog of ax by minus ay bx in 2 dimensions. We have now, because there are 3 components possible, you can choose them 2 at a time, and this is what you get. I choose xy, I get this, I choose yz, I get this, I choose zx, I get that here. It turns out that when you compute what these quantities do, it turns out that this set of quantities transforms exactly like a vector does under rotations. So this means that if you call for the moment this quantity here to be a component of a vector c subscript x, c subscript y, c subscript z, these 3 quantities qualify to be a vector in the sense that they transform exactly as the coordinates x, y, z do under a rotation of the coordinate axis about the origin. Therefore, these 3 are components of a vector formed by taking the vector a and b, combining them in this bilinear fashion to produce a new vector whose components are precisely these combinations here. So the x component is yz minus zy, the y component is zx minus xz, and the z component is xy minus yx in cyclic permutation. This quantity is called by definition the vector product of A and B. There is one component of A in every term, there is one component of B in every term, and it is called the vector product here, or cross product for this cross. In contrast to the dot product which produced a scalar, the cross product produces a vector in 3 dimensions. In 2 dimensions it did not, the analog just produced a pseudo scalar, but here it actually has produced a vector under rotations here. Now one could ask, just as if I took 2 arbitrary vectors A and B and there is a certain angle theta between them, I also know that A dot B, instead of writing it in Cartesian components, I could also write this as the magnitude of A times the magnitude of B times the cosine of the angle between them. In exactly the same way, can I write some formula for A and B given 2 arbitrary vectors A and B of that fashion, of that kind in 3 dimensions? And the answer is yes, but now you have a vector. And what is the meaning of this thing? Geometrical meaning. So let me write this. Geometrical meaning of this turns out to be the following. From A and B you can form a parallelogram. Let us draw this again. So here is A, there is B, and you can extend this and form a parallelogram, and it turns out that the area of this parallelogram is given by the magnitude of this vector, and the direction of this vector happens to be the direction normal to this parallelogram. You are already aware of the fact that if I took this triangle, the diagonal here, this area is equal to that area, and if this angle is theta, then the area of the triangle is equal to half A times B times sine theta. We know that from elementary geometry, and of course the area of the parallelogram is twice that, so it goes away here, and the parallelogram area is equal to AB sine theta, and that is exactly what the modulus of A cross B is. On the other hand, the direction of A cross B is perpendicular to the plane of this parallelogram in this direction, and that direction is found by taking A and rotating from A to B through an angle theta in the direction of a right handed screw. The direction in which the right handed screwdriver moves up is the direction of this vector A cross B. So this is the vector A cross B, and therefore A cross B equal to the magnitude of A cross B equal to AB sine theta, the magnitude of A sine theta here, and the direction of A cross B is along the normal to this parallelogram in the sense in which a right handed screwdriver moves when you rotate from A towards B. So if A is coming out here and I rotate into B, then the screwdriver moves up, and that is the direction of the vector A cross B. Okay. So we have a prescription, a geometrical meaning, which will tell us not only the magnitude of A cross B but also the direction of A cross B in this fashion. Now this construction is peculiar to 3 dimensions, because in 2 dimensions the analog produced a pseudo scalar, but in 3 dimensions it has produced a vector. And it turns out in higher dimensions it does not produce a vector in those dimensions, it produces something called a tensor, which we are not talking about here. But the fact is that in 3 and only 3 dimensions is the cross product of 2 vectors going to produce another vector, and that is a very profound observation, a very important one for all physical problems, in many physical problems. Okay. Now that we know that, is there any difference at all between this kind of vector and the kind of vector that the coordinates are, or any of these vectors here? Is there any difference at all? Well, yes, indeed there is, because look at what happens under parity. If A and B are proper vectors, under parity A goes to minus A, B goes to minus B. A dot B does not change sign and it is a scalar, we already established that, but A cross B is going to remain unchanged in sign, and yet it is a vector. We already said under rotations A cross B behaves exactly like the position does or the velocity does and so on, and therefore it is a proper vector. So if A and B are proper vectors, A cross B is a proper vector under rotations, but under parity it does not change sign, whereas all vectors change sign. Therefore we have two kinds of vectors in 3 dimensions. We have those which change sign under parity and those which do not change sign under parity. All these are vectors. They are also known as polar vectors. And the class of vectors which change sign, they are called pseudo vectors or axial vectors. And these are the cross products of any two ordinary vectors. For instance, R cross P equal to the angular momentum. That is an axial vector. It behaves exactly like a vector does under rotations of the coordinate axis, but the moment you have a parity transformation, it does not change sign, unlike what a vector really does. Okay. What about R cross V? Well, it is going to do exactly what this does, because V and P just differ by this constant multiple here, and so on. So whenever you take two vectors from this column here and take the cross product of the two, you are going to get an axial vector out there. For instance, if you did R cross F, this is equal to tau and it is equal to the torque. So the torque is an axial vector, the angular momentum is an axial vector, the cross product of any two vectors here is an axial vector there. What happens if I take L, an axial vector, and take a cross product with R? Well, now that is easy to write down what is going to happen, because if you look at R cross L, under parity this goes to minus R cross and it remains L. So that is equal to minus R cross L, and therefore it is back to being a polar vector once again. So if you took the cross product of a vector from here and a vector from here, an axial with a polar vector, you are back to a vector, a polar vector. If you took the cross product of two axial vectors, what do you think will happen? If I took L cross tau, for example, or L cross any other vector here which is an axial vector, neither of the axial vectors changes sign, so it remains an axial vector in this case. But the moment you take something from here and something from there and take the cross product, you are back here in this direction, back to an ordinary vector. Well, we can write down using exactly the sort of input we wrote, namely using Newton's law. We wrote down, for instance, what the electric field, what the angular momentum does, or what the torque does and so on, the force does. We can now write down what the electric field would do. For instance, I know that if you have a charge Q and I apply an electric field E, then the force on this electric field is Q times E. So if this is a point charge and this is the electric field applied, I know that the force on it is the charge multiplied by the electric field intensity. Since this is a scalar and I know that is a polar vector, this is a polar vector. So I add to my list electric field E. What about a magnetic field? Well, that is a little more complicated. When I apply a magnetic field B on a charge Q and the charge is in motion, then the force, the magnetic force on this charge is q times the cross product of V with the field B. That turns out to be the force, it is called the Lorentz force on a charge which is moving in a magnetic field which is applied. Now I know that this is a polar vector, that is a scalar, this is a polar vector, that therefore has got to be an axial vector because this quantity will change sign under parity. It will become minus f, and if this law is to remain the same whether I change coordinate system from a right handed to left handed coordinate system or not, this has to become q times minus V cross B. The minus signs have to cancel out to give me exactly the same law in the old and new frames, which tells me that B cannot change sign. So the conclusion is that the magnetic field B is an axial vector, and so on. So we can actually fill up this list from one to the other. We logically deduce using a law each time which brings in a new physical quantity. We can classify whether the new vector that we are dealing with is an axial vector or a polar vector. But remember that as far as rotations are concerned, there is no difference between a polar vector and an axial vector. It is only when you bring in an improper transformation such as reflection or parity that there are changes of sign. But it is a very valuable thing to keep in mind because it again serves as a consistency check and tells you there are subtle differences between quantities of one kind and the other. By the way, if you took the dot product of something here and there, what do you think is going to happen? If I took for instance the electric field E and did a dot product with B, that we know has to be a scalar, it is a scalar product. This however is a polar vector. This is an axial vector, and this combination under parity becomes minus E dotted with plus B and therefore changes sign. And what have we called a scalar quantity which changes sign under a reflection, under a parity transformation? We called it a pseudo scalar. So this thing here is not an ordinary scalar, it is a pseudo scalar. So in this fashion we can actually write down the transformation properties of various physical quantities once you have a small dictionary which tells you what some basic quantities transform like. So we will continue with this, and we will continue to keep this in the back of our mind that there are two kinds of vectors in 3 dimensions, and the cross product of two ordinary vectors or polar vectors is actually an axial vector. It is a slightly different kind of vector, but there are physical quantities which are either polar vectors or axial vectors, and they have their own importance. Alright, so this is useful information to know. We still have some way to go in understanding vectors in 3 dimensions. The next task will be to see what some of these basic formulas are.